Hi, now what I've got here is a velocity time graph for a train leaving a station, building up speed at a constant rate, then it goes at the same speed and then starts to slow down at a constant rate to stop at the next station. Now, a graph like this isn't really very realistic because when a train leaves a station, it's very likely that it's going to slowly build up its speed, and when it gets to this part where it maintains a constant speed, it's going to gradually approach it rather than this sharp turn here. And the same applies as we come down here. The train's moving at a constant speed, then it's going to gradually slow down and come to rest. The graph is going to most probably look something like this. So you can see it's not made up of our straight lines except for this section here where it maintains a constant speed. So what would the corresponding displacement time graph look like for something like this? Well, it's going to look like this. Over this section where it maintains the constant speed, this part's going to be a straight line. And over this section, our displacement graph's going to look like this, bit curved, and similarly as the train comes to rest, the graph's going to look something like this. Now we've seen in the past that gradient on the displacement time graph gives velocity. That's all very well when we've got a straight line like this. Very easy to get the gradient. Just simply create a little triangle in here and work out the change in velocity divided by the change in time. But on sections like this where it's curved, how are we going to work out what that velocity is? Well, if we know the equation of the curve, let's say s is some function of time, then to get the gradient, let's just put a point here, say, that we're interested in, we need to think of what the gradient of the tangent is at that point. And the gradient of the tangent is given by the rate of change of displacement. We have to use calculus. V equals ds by dt, in other words, the rate of change of displacement with respect to time. On this section here, we would find that the velocity given by ds by dt was a constant, never changing. So in other words, if we want to find the velocity from any displacement time graph, then all we need to do is to differentiate the displacement time graph then with respect to time, ds by dt. Now once we've drawn our velocity time graph, remember we saw that gradient always gave acceleration. So therefore, if I wanted to know the acceleration over this period, I could work out the gradient, say, of the red line. But what happens when we've got a curve? Well, just the same kind of thing as we did down here. We need to differentiate with respect to time. So for instance, if I was looking at the acceleration at this point here, I would need to work out what the gradient of the tangent was at that point. In other words, acceleration is the rate of change of velocity with respect to time, dv by dt. And at this point here, the acceleration, because it's going at a constant velocity, acceleration, or dv by dt, we would expect to be equal to 0, no gradient at all. So when you want to work out acceleration from velocity, all you've got to do is differentiate velocity with respect to time. So that's all very well. But we can actually reverse the process. If we've got acceleration, we can get back velocity. To get back velocity, all you need to do is integrate, do the opposite of differentiating. So you integrate the acceleration with respect to time. And similarly, if you want to get back to your displacement equation, S, you can integrate the velocity equation. So in other words, S will be equal to the integral of the velocity equation with respect to time. Now we'll do some examples later on for you on this, so don't panic too much on this, okay? But just if you can remember these ideas, hopefully working through the examples in the next video will bring this out a lot more. Now it's also well worth noting that S is the integral of v with respect to time. And if we were to take our graph for v and were to integrate it, well, when you integrate a curve, you're actually finding the area underneath it. And can you remember that the area under the curve gave the distance? So we have the fact that integrating our curve gives S the displacement. I know I said distance here, but remember, if it's above the t-axis, displacement and distance will be exactly the same thing. It's also well worth noting that when we want to find the acceleration, we differentiated the velocity with respect to time. But what was velocity? Well, velocity is ds by dt. So you are differentiating ds by dt with respect to t. And this is often referred to as d2s by dt squared. So you might find on occasions that you need to use this. Now hopefully all this kind of idea will become a lot clearer when you look at the examples which follow in the next few videos.